Okay, so last time we talked about conservation principles through two examples, one in which the conserved quantity was the sum of the 4 positions of the 4 coins, the other in which the area of the figure formed by those points was the conserved quantity. So we will talk about a few more examples this time. So let us do the following, let us again talk about examples on the plane. So what is our initial configuration going to be? So let us now take 3 points which form, let us say, a right angle triangle. So here are 3 points A, B, C. So those are my initial point. So my configurations here are triples of points like this A, B, C, and in this case the initial configuration is where they form a right triangle. And of course now we need to give the evolution rules. How do how does the system change with time? So how do the positions of these 3 points change with time? Well, here is what you are allowed to do. So what are the allowed moves at each time? You can apply any one of the following. Can apply any one of the following transformations. You can apply a translation, you can apply a reflection, a rotation, or a dilation. So these are examples of transformations we talked about. So by dilation I mean a uniform dilation. Okay. So these are the 4 operations or allowed moves that you can perform. So you can translate this triangle, you can reflect it about any line, you can rotate the triangle, or you can dilate the entire triangle. Okay. So and you can, at each time you pick any one of these 4 operations and you perform it. That is the idea. Now here is the question, is it possible that at some point of time t that you land up with an equilateral triangle? So the question is, can this system reach the following configuration, one in which the 3 points lie on the vertices of an equilateral triangle. Okay, so imagine this is an equilateral triangle. Okay. So that is the question, can it somehow reach this configuration? Okay. So again the attempt to answer such questions lies in trying to find something that is conserved during the evolution, something that does not change, and in this case it is easy to answer because we have of course studied these in depth. Here is what we know, a translation or a reflection or a rotation gives you a congruent triangle, right? It does not change lengths or angles, so what you get is just a congruent triangle, whereas dilations, a uniform dilation, will not preserve lengths, but it will certainly preserve angles. So it will give you a similar triangle. So that is something we looked at. So another way of stating this is you keep track of the 3 angles of this triangle. The 3 angles, the list of the 3 angles is conserved. So how should we, so if C denotes a configuration, so here the configuration is just the 3 points, the 3 vertices of the triangle. What is a gamma function if you wish? The gamma function can just be the list of the 3 angles. So this is just the angles at the points A, B, C. Okay. So here the conserved quantity is not just one quantity if you wish, but rather a list of the 3 angles, but nevertheless observe that the evolution rule conserves gamma. So observe that gamma is in fact conserved during the evolution. In other words, no matter which of these moves you apply, what you will get will be a triangle which has the same 3 angles. Okay. So it will continue to remain a right angle triangle throughout, in which the top angle of course is also equal to whatever this is. So it will, if the 3 angles are 90 degrees alpha and beta, the same thing will continue to hold for every triangle that you get during the evolution. Okay. So you cannot get an equilateral triangle, that is basically the conclusion here. Okay. But the key point is really in figuring out what the conserved quantity is, which in this case is, for instance, the 3 angles. Now here is another example where we will not look at all the transformations we wrote out, but only about rotations. So let us only look at rotations. So again here the same thing. So what is the initial configuration here? Here instead of taking a triangle, let me just say initial configuration is just some point Okay, so I have a point on the plane, that's my, so the coordinates x and y, we call it x0, y0. This is the initial configuration. Okay, my system consists of just the point, and I should tell you how the system evolves. So how do I transform it at each instant of time? Well, I apply a rotation to it. Okay, so what's the allowed move? Is you take this point and you rotate it through some angle theta. So rotate it meaning you join it to the origin, and then you rotate this by an angle theta. Okay, and doing that will give you another point. That's the new configuration of the system. And similarly, at the next instant of time, you again pick some random angle theta and you rotate this by the angle theta. What you get is again a new configuration. Okay, so in this case, just from this geometrical description of the system, here's what the system typically goes through. It starts out at this point, maybe you rotate it through a certain angle, and then at the next instant you rotate it by some other angle, and so on. So it keeps sort of moving around on the circle, occupies various positions depending on what angle theta was picked at that time instant. Okay, so that's the evolution of the system. And now here's the question, what's the conserved quantity? So of course, remember rotations, you know, they certainly do conserve areas and things like that, but more importantly they preserve lengths. So here, so what's an allowed move? So let me just write that out. An allowed move is you are allowed to apply the rotation. Let's give the rotation, it's a linear transformation by the angle theta. So what rotation are you allowed to apply? So r theta has the following formula. So it's something for you to check. This is just cosine theta times x minus sine theta times y, comma cosine sine theta x plus cosine theta y. So what you are allowed to do at each instant of time is to pick an angle theta and apply this transformation to the point xy, okay, thereby obtaining another point xy. Of course, it's much easier without the formula. It's easier just geometrically to see. What you're doing is just moving it to a point which is rotated by an angle theta. Okay, so you apply a rotation. So now here's what's the conserved quantity. So let's define the function gamma for a configuration. So what's the configuration here? It's just the coordinates of the point. Okay, so the configuration C just denotes the point that you have, and we will define the gamma function to be the length or the square of the length. Okay, so let's define the gamma function to just be the length function if you wish, and the key thing here is that rotation preserves lengths. Okay, so observe that gamma is conserved under the evolution, is conserved as the system evolves. And why is that? Well, because if you wish you can just actually check this by calling this as x prime and that as y prime. So let's just write this out one step. I'll just leave the verification to you. Call the x coordinate as x prime. So this is just sort of a verification from the formula. As I said, geometrically it's pretty clear that the length is preserved, sine theta x plus cosine theta y. So that's the new position or the new configuration of the system. And now if you just compute x prime squared plus y prime squared, you will find that the identity cos squared plus sine squared is 1 will help you prove that x prime squared plus y prime squared is 1 is equal to, sorry, x squared plus y squared. Okay, so check this. So here's a conserved quantity. So for instance, this in particular proves that if as the system evolves, if you start out with a point at a distance 5 from the origin, the system can never reach a state where that point is now at a distance 10 from the origin. Okay, you are constrained to stay within the distance 5 from the origin. So those are the only possible configurations that you can reach. And here's a minor tweak of this example that I'll leave for you to try. So this also involves the so-called hyperbolic functions. So let me just recall what are called the hyperbolic cosine and the hyperbolic sine. So in case it's not already familiar, so cosine hyperbolic of u, so u is any real number here, is defined to be the following: e power u plus e to the minus u divided by 2, and sine hyperbolic, so hyperbolic sine is defined as e to the u minus e to the minus u divided by 2. Okay. So there is a hyperbolic version of the previous example. Okay. So there we said the configuration. So now here's the system I want to study. My configuration again is just a single point. So for instance I start out at some point x naught y naught, and now how do I evolve the system? So what do I allow? So here's the allowed move. You are allowed to apply the following transformation. So at each time apply a transformation, let's call it tu for some value of u. Okay, so you pick u, you pick a real number u, just as in the earlier example, what is the allowed move? You pick an angle theta and then you rotate by the angle theta. Okay, you apply the transformation which is rotation by theta. Similarly here you pick a real number u and then you apply the transformation tu which I will just describe. So pick a real number u and apply the following transformation. So what is this? Just like in the earlier case, here's the definition of tu. It takes the point xy to the following point: cosine hyperbolic u times x plus sine hyperbolic u times y, comma sine hyperbolic ux plus cosine hyperbolic uy. It's almost like the earlier one where we had cosine minus sine, sine and cos. Here it's just cosine hyperbolic, sine hyperbolic, sine hyperbolic, cosine hyperbolic. Okay, so this is the allowed transformation. Okay, so at this point we don't yet have a very geometrical idea of what this does. Okay, so it's not like a rotation or any such thing. Okay, it's somewhat different. Now again the question is really the following: can you find a conserved quantity for this evolution? So here's the thing that I'd like you to check. So here's the conserved quantity. So what's the configuration? As I said, it's just the point, coordinates of the point, and define gamma of c in this case to be x squared minus y squared. Okay, and prove that. So check. So this part is the exercise. Check that gamma is conserved. And how do you do this? You have to do pretty much the same calculation we did earlier. You call this as x prime and y prime, the two. So these become the new coordinates of the new configuration of the system, and you will have to check that for this new x prime and y prime, the difference x prime squared minus y prime squared however remains the same as the old difference. Just like we checked for the cosine and sine case, that the sum of the squares remains constant. Here after applying tu you get a new x prime y prime whose difference of the squares remains a constant. Okay, so what does this really mean? It says the following geometrically, that suppose the original system, the initial configuration, suppose you were at the point 1 comma 0, then the gamma function corresponding to your initial configuration is just 1 squared minus 0 squared. Okay, so you are at, the gamma function is a 1 in this case, and what it says is as the system evolves the gamma function cannot change. So no matter what your new point is, x prime comma y prime, the difference of the squares had better be a 1. Okay, so x prime squared minus y prime squared in this case must remain a 1 because that's what it was at the initial point of time. So what this means is, so observe, this is the equation of a rectangular hyperbola, so which sort of looks like this. There's also another branch on the other side. Now this hyperbola here is the constraint, meaning the point, the configuration of the system is constrained such that it can only lie on this particular hyperbola. It can't move anywhere else. You can't get other arbitrary points on the plane. You are always constrained to only lie on this hyperbola. Okay, so at each time it can give you a hyperbola. Similarly, in the earlier example, what was the corresponding thing in the earlier example? That was a circle. So if your initial point is 1 comma 0 in the previous example, then at each time t you are constrained to lie on the circle of radius 1. You cannot move out of this circle. Okay, similarly, in this case you cannot move out of the hyperbola. Okay, so these are all examples of conservation principles in what you might call discrete systems, meaning I am not thinking of time as being a continuous variable, I am only doing something at time t equal to 0, t equal to 1, t equal to 2 and so on. Now the conservation laws that you are likely to have heard of before in the context of physics, classical mechanics especially, are there. Of course time is a continuous variable, right. So you imagine that time varies continuously, and as t varies there is a system which varies continuously with time, but no matter how it varies there are some quantities which are conserved. Okay. So let me just make some brief remarks about conservation principles in the context of classical mechanics. So here is the various conservation laws that you might have seen, especially for instance the law of conservation of momentum. So this is in fact an instance of the sorts of conservation principles we are talking about. So this is often called the law of conservation of momentum. So again, what is the setup there? You have a system, so it's a system. Classical mechanics, it could have a bunch of particles and so on, but there is of course one important restriction here, that this system is not being acted upon by external forces. So system not subject to external forces. Okay, and system is probably in some initial configuration. So there are various particles moving in various along various directions. So they have various momenta, for instance. So this could be the picture of the system. Now the particles themselves are interacting. So there are, so how does the system evolve with time? The evolution is according to, well, the laws of classical mechanics, if you wish. So the evolution is according to, so what are the rules for evolution? So in our case we wrote them out as certain allowed moves. We said, okay, these are the things you can do to change the state of the system. Now in the case of classical mechanics, the laws of mechanics, or for instance if you wish Newton's laws, which are essentially some differential equations. So the evolution is by certain laws of mechanics, for instance Newton's laws. But what are these, just written out mathematically? Well, these are actually certain differential equations. So these differential equations tell you how the system changes with time. Okay. So they will be given by, say, the derivative of the momentum is the force and so on. So there are some rules which tell you what the trajectories are that these particles take, and there are rules for how they interact and so on. So these differential equations govern the evolution of the system. Now here the conserved quantity is something which has the following property, that no matter what the differential equation tells you happens to the system, the momentum, the total momentum of the system can never change. Okay. So the form of the differential equations is such that even though the system changes with time t, the total momentum cannot change. Okay. So at the end of the day the conserved quantity very much depends on what the rules for evolution are. Right? That is the thing that we have seen throughout. In the very first example, the evolution rule was something special. You had what we looked at last time, a couple of coins picked out and moved equally and moved by the same amount in opposite directions. That very special form of the evolution rule guaranteed that the total sum of the positions would remain constant. Similarly, if in the case where we had transformations certain allowed transformations of the plane, the only allowed transformations were all things which had determinant 1, or at least absolute value of determinant 1. So the total area was conserved. Okay. So the fact that you had a very special restricted set of evolution rules is what guarantees, or is what allowed us to find certain nice conserved quantities. Now similarly here the rules of classical mechanics or the differential equations have this very nice form, assuming there are no external forces. This sort of guarantees that things like momentum, or in other contexts the law of conservation of energy and so on. So these rules guarantee the existence of certain conserved quantities. That is sort of the broad moral of the story. Okay, so we will talk about matrices and other things next time.